Welcome to the session on separation logic and memory semantics. And the first talk we have is on separation logic for managing resources in higher order concurrent programs. And Daniel Gratzer from Aarhus University is going to present it.
I'm presenting iron. This is joint work with Alish, myself, Robert, and Lars. And let's get straight into it. So the problem that we're interested in is that of obligations. So when programming, when we use certain constructs, they impose upon us duties to perform certain actions at a later point. So if we acquire memory, we need to release it. File handles that are open need to be closed. Locks that we grab, we need to let go of them eventually. And these things don't fall under the banner of partial correctness specifications, but they're important, practically speaking, to writing programs that work as we intend them to. However, concurrency complicates this. In order to show this, I have a tiny little program here, and I want to walk through it. So in this program, we start by creating this channel that we're going to use for communicating between two threads. It's a reference cell. It can be none if there's no message, or some if one message is put into it. And then we fork off a thread, and this thread is just going to spin, waiting for a message. And the main thread, eventually, will send it a message. And that message is going to be just a freshly allocated reference cell. Once the message has been sent, the forked off thread should see it. It's going to free the message, the reference cell, and then free the channel itself. And we have two refs and we have two frees. So intuitively, this program shouldn't leak anything. However, it's a little bit complicated to actually prove this formally, especially because we're allocating memory in one thread, we're throwing it over to another thread, that thread deallocates it. It's hard to make sure that nothing gets lost in the shuffle between all these concurrent threads. Our proposal for proving this is to develop a concurrent separation logic to help us. And we want this concurrent separation logic to satisfy several properties. We want thread local reasoning and modular specifications so that when we prove larger programs, things compose and we don't have to study the entire program at all points. We also want to handle complicated language features, in particular fork. So on the last slide I used fork, which just throws off a thread which runs concurrently indefinitely. And I also want our concurrent separation logic to be amenable to mechanization, because these proofs get tedious and involved. And it's helpful to have a proof assistant that checks all these details for us. And of course, at the end of the day, we want to be able to use this concurrent separation logic to prove leak freedom. Now, to my knowledge, there is no concurrent separation logic that satisfies all of these points simultaneously right now. But we do at least have Iris, which is going to give us the first four. And so we're going to build on this to try and satisfy the fifth. So our contribution is twofold. Firstly, we have a general notion of trackable resources. This is independent of Iris or any concurrent separation logic. It's just an idea that we propose for managing obligations and ensuring that they've been correctly handled. And to show that trackable resources are actually useful and scale to some proofs, we've developed iron, which is a particular concurrent separation logic, which includes all of the proof techniques of Iris. It supports all of the language features that Iris supports, in particular fork, and all of the proofs for iron are fully mechanized in Coq. So I mentioned earlier that Iris doesn't quite give us what we want. So what goes wrong? Well, the issue is that Iris is affine. In particular, this means that if we have P star Q, we can drop the Q and just prove P. At any point in time, we're entitled to take some resource and drop it on the floor. And this means that we get an adequacy theorem kind of like the one that I have up here, which basically says that if we specify some program as true, E true, then E at least is not going to crash. It's not going to get stuck in some weird way. But I want more than this. I also want to prove leak freedom. On the other end of the space, we have concurrent separation logic, which does let us prove leak freedom, but only for statically scoped concurrency. That is, only for par. So in concurrent separation logic, we only have parallel composition, we don't have fork. And the way that we ensure leak freedom here is we have emp, which in Iris is completely degenerate. But emp specifies that our view of the heap is empty. So if we specify a program with emp emp, then we know that it doesn't leak. So why can't we just adapt concurrent separation logic to work with fork? I mean, it seems like it's sort of what we want. The issue is actually in the rule that I don't have here. Because this rule for par on its own, it's not going to be sufficient. It doesn't allow us to share memory. In order to do that, we need invariants, which allow us to determine protocols around shared pieces of memory. In CSL, we have a particular notion of invariant, which I'm calling scoped invariants. And the rule for them, well, one of them at least, is written on the slide right now. And it basically says that within a particular block of code guarded by this resource RIN, we can take some invariant, we can throw it into the context so it can be shared amongst threads, we can execute E, and then at the end of the day, we get R back. Scoped invariants are fine when we just have par, but once our notion of concurrency is unscoped, like it is for fork, these invariants aren't quite enough. So I have an example program which demonstrates this. So we start by allocating a location. We then throw it into a invariant guarded by R, and we fork off a thread which just reads the cell. And it uses the with RDo to ensure that it's safely accessing this cell. And once we get out of the block guarded by resource RIN, the invariant is deactivated. We get the location L back in our main thread, and we free it. So this is perfectly specifiable if I just sort of naively adapt CSL. But the issue is it can crash. There's a race condition. The forked off thread might not get scheduled until after the main thread, and then we're in trouble. So this is not a new problem. This already comes up in Iris even when we're not worried about proving leak freedom. In order to handle this in Iris and other logics, we have unscoped invariants. And so the rule for allocating unscoped invariants looks more like this. Basically, you take some proposition R and you just throw it in an invariant. And it can be shared, duplicated freely. It's not governed by a particular scope. It's just there forever. And this is nice. We can duplicate it freely, share it amongst threads, send it to threads that didn't previously know about it. But there's no explicit deallocation rule. We can encode it, but it's not there by default like it was for CSL. But there's actually a bigger problem, which is that we can always take a resource and stick it in an invariant and essentially forget about it. Which means that once we have unscoped invariants, just having linearity in our logic, having emp, is going to be deeply problematic. We can usually circumvent it in some way. So at this point, we have like this sort of tension seemingly between linearity and our invariants. We have scoped invariants, which handle obligations well, but they don't handle fork. And then we have unscoped invariants, which are perfect for fork, but at the same time, they allow us to leak resources, which we don't want. And also, invariants are kind of complicated to prove correct. They're usually one of the most intricate parts of concurrent separation logics. So if possible, I sort of don't want to invent an entirely new notion of invariant. So instead, what we propose is to modify the other connectives of the logic to make unscoped invariants work. In particular, I'm going to modify points to. So what we're going to do is we're going to keep the logic affine, like Iris's, so that unscoped invariants still work, but we're going to index points to by a fraction. That fraction goes from 0 to 1, and that's exclusive inclusive. And we also add a new proposition, emp of pi. And this pi indicates how much of the heap we get to know about by owning these propositions. Okay, so what does that mean? If we own L points to V at 1, then I know that the only thing in the heap is this location. If I own emp at 1, then the heap is just empty. On the other hand, if I own L points to V at some pi that's less than 1, I basically don't know anything about the heap besides the fact that it at least contains this location. So in particular, this isn't a proportional thing. If I own L points to V at 1/2, I don't get to know that there are at most 2 locations. It's just a logical bookkeeping thing. On the other hand, they do add properly. So if I have a set of permissions which sum to 1, then I get to know that I fully know the heap. And this gives us a methodology for actually proving stuff. Because at the end of the day, we're going to gather up all of our fractions. We're going to create emp1. And then we're going to conclude that the heap has to be empty, and we'll have proved leak freedom. So there's an obvious question, which is this the same thing as fractional permissions somehow? And the answer is no. So in concurrent separation logic, we have fractional permissions for dealing with multiple readers and one writer. So if you own L points to V at pi with fractional permissions, this means you own pi of this location. In iron, if you own pi at L points to V at pi, that's pi of the entire heap. And so we're entitled to write to any points to regardless of whether or not the fraction is 1. That's different than fractional permissions. So with that in mind, let's look at some new rules. So the idea here is that we basically instrument the standard rules with fractions. So if you have permission for some empty heap, we can allocate a new reference in it, and that reference gets the same pi as the empty heap had. When we free something, it's exactly the opposite rule. The rules for reading and writing, they're exactly as they were without fractions. We've just added pi's everywhere. In particular, the rule for writing doesn't require that the fraction is 1. We also have some new rules for just manipulating these new fractions, and we can sort of push them around and split them. So if we have an empty heap, we can split it apart into 2 empty heaps as long as the fractions sum back together. And if we have points to, we can push a fraction out into an emp or push it back in. So we can sort of manipulate the concrete numbers. Now, I got into all of this because fork was difficult to specify. So what happens with fork? Well, there's a standard rule for fork, which is that if E doesn't crash, then if I fork off E, things still don't crash. And we get that rule, but it's not enough anymore. And it's not enough in any of the interesting cases in particular. If I fork off a thread that never joins, I'm not going to be able to specify it properly. So here's a very common example, I think, of a concurrent program, where I fork off a thread, I allocate, and then I immediately deallocate, and then in the main thread I just add 1 and 1. But the issue is, in order to specify this, I have to give the forked off thread some emp of pi, because otherwise it can't specify these allocations. But at the end of the day, that emp of pi is just going to be lost. It's never going to be joined with the main thread again, and so I'm not going to be able to produce emp at 1 like I want to prove leak freedom, even though this doesn't leak. So we need a slightly stronger rule, namely that if we fork off a thread and that thread terminates with emp of pi, I get that emp of pi back in the main thread right away, and I can use it to establish the final post condition. Now, all of these rules are only interesting because they actually tell us something about when programs run. So what happens when you specify a program in iron with emp pi, E, emp pi for some pi? Well, I still get the old thing, which is that E is not going to get stuck or crash. But I also get a new thing, the second fact, which says that if I run E on some heap, and E terminates, and all of the forked off threads that E creates terminate, then the old heap has to be exactly the same as the new heap. So if I start this on an empty heap, I'm going to allocate a bunch of memory, but by the end I have to have freed everything and gotten back to the empty heap. I can't have leaked anything. Now, the logic still isn't linear. I can still take things and drop them on the floor, but if I do that, I'm not going to be able to apply this adequacy theorem, because this adequacy theorem requires that I gather up all of the pieces of pi at the end of the day. If I drop some points to, I'm going to lose that part of the pi. So at this point, iron is a thing. It's useful. We can prove stuff in it. But it's sort of annoying to use because these fractions add tedious bookkeeping to every proof. So here's a little program that should be somehow trivial to specify and prove. And the difficult part of this isn't the program. It's that we have to prove some stuff about fractions. And I don't think I need to sell anyone here on building better tools to make proofs easier. So that's what we're going to do. So in particular, we're going to take the specification logic of iron, and we're going to lift it so that propositions are actually functions from 0 to 1 to other propositions. And we lift the connectives of the specification logic to these functions. And in particular, now P star Q at pi means that we just split pi somehow and give part of the pi to P and part of the pi to Q. We ignore the concrete choice of splitting. Similarly, we can lift points to so that the pi is factored out, so that we don't have to look at it when we're actually doing proofs. And this lifted logic is actually a linear logic. We've taken an affine logic and built a linear logic on top of it. And the reason for this is basically, if we prove something like this, we're required to forget some part of the pi at which we're proving it, and that's illegal in our logic. Now, the program logic becomes a lot cleaner in this lifted logic. In particular, we get a lot of the rules from standard linear separation logic. So we have emp, we allocate, we get L points to V. If we free, we get to drop the points to, and we get emp back. But I want to point in particular to the rule for fork, which I think is quite clean. It says if you fork off a thread that doesn't leak, the whole program doesn't leak. Now, in the lifted logic, we have a specialized notion of invariant to make things a bit cleaner. And these invariants are different in that they come with an explicit permission for opening them and an explicit permission for deactivating them. And if you own all of the opening permission and all of the deactivating permission, you can just cancel it. This is sort of a common pattern in iron because you put some stuff in an invariant, you run some concurrent code, and then at the end of the day, you want to get stuff out of the invariant so that you can manage to dispose of it correctly. And these invariants capture that. But they're slightly limited. They don't let us prove everything. So sometimes we need to drop down to the unlifted logic to prove things. So to prove this implementation of par using spawn and join. So spawn and join under the hood, they're going to fork off a thread, compute E1, write it to some shared cell, and then join is just going to spin waiting for that write to happen. In order to prove this, I need to drop down to the unlifted logic, but I provide specifications for it in the lifted logic. No one who uses my proofs need care that I use slightly lower level methods to prove it. And so this allows some compositionality. In particular, when we've used iron, we've been able to verify almost everything in the lifted logic. So all of these examples, except the first one, are fully in the lifted logic. So we formalized a transfer, some examples of resource transfer. So that's sort of the thing that we saw at the very beginning, forked off threads, throwing memory back and forth. We've also formalized a messaging system that allows for asynchronous messaging. So you have two threads, they talk to each other, and at any point they can give up talking to each other, and at that point a background thread will come in and free all the memory that's left. And we've proven all of these in the lifted logic, and we can show that none of them leak memory. So, wrapping up, we presented trackable resources, which is this idea for managing obligations using these fractions to make sure you can explicitly tell when things have been dropped. And we've shown that this idea can scale reasonably well using iron, which allows us to formalize interesting examples and mechanize them. And some of them we can even do without having to pay explicit reference to the fractions. Everything can be found online at this URL. So thank you.
All right, have plenty of time for questions. Let me start from the anonymous one from Slido. Simple question, do assume program termination?
Yes, so these are partial correctness specifications. The adequacy statement assumes that the program terminates. We're interested in proving similar things for non-termination. That's ongoing work in Iris in general.
Thank you.
Or proving termination, rather.
Anyone? All right. Oh, Carol?
So, what if I need to use an unscoped invariant? Can I use any of this?
Yeah, so the idea is that for unscoped invariants, or just using Iris's more general notion of invariant, you'll drop down to the unlifted logic, you'll do some stuff there, and then you're going to prove lifted specifications so no one needs to see what horrible thing you've done.
All right, another anonymous question. If your language had futures, could you use the same logical mechanisms to reclaim resources upon resolving them?
I suspect we could implement futures using fork, just by forking off a thread and writing to a shared reference, but maybe I misunderstand.
All right. While the next speaker is preparing his talk, I have a question. So in the recent works, Schwang-Barclay and Aquinas-Hobor observed certain limitations of fractions to be rational numbers, and they used fractional tree shares instead. Did you consider using them for pies or?
No, but I'd certainly be interested in seeing what that could offer us. So, thank you.
All right. Well, let's thank Daniel again.